What is a diaphragm wall? Welcome to Civil Engineering Edge, where we break down complex engineering concepts into clear, practical knowledge. Today's topic is the diaphragm wall, a critical element in modern deep excavation and underground construction. So, what exactly is a diaphragm wall? A diaphragm wall is a deep, reinforced concrete retaining structure, typically built in situ. It's constructed by excavating narrow, deep trenches and filling them with reinforced concrete. These walls are generally between 500 millimeters to 1,500 millimeters thick and can go as deep as 60 meters or more, depending on the project needs. Diaphragm walls act as permanent or temporary barriers in geotechnically challenging areas, especially where groundwater or unstable soil exists. They serve both structural and water cutoff functions, making them ideal for basements, subways, tunnels, shafts, and deep foundations. The specialty of diaphragm walls lies in their ability to be constructed before the excavation of soil. This pre-support provides great stability, reduces deformation, and minimizes the impact on surrounding structures. Stay with us as we explore its uses, design principles, construction techniques, and the state-of-the-art machinery that brings these walls to life. What is the diaphragm wall used for? Purpose and is code. The diaphragm wall serves both structural and geotechnical purposes, primarily in deep excavations and waterlogged soils. Its key applications include construction of deep basements in urban environments, earth retention during underground metro or rail tunnels, cut-off walls in dams or shafts to control groundwater flow, permanent retaining walls for high-rise structures. But why is it preferred over other methods? Diaphragm walls offer minimal ground movement, making them ideal near sensitive structures. Their watertight nature, when combined with Bentonite slurry, provides excellent seepage control. Additionally, they serve as permanent structural components, eliminating the need for secondary retaining systems. From a design and construction point of view, diaphragm walls are versatile, durable, and space-saving. IS code reference. The design and construction of diaphragm walls are guided by IS 9527 Part 1 and 2, Code of Practice for Design and Construction of Diaphragm Walls. For structural design, IS 456-2000 and IS 3374 water-retaining structures are also relevant. As we move ahead, let's look into the structural analysis guidelines essential for safe and efficient diaphragm wall design. Guidelines for structural design, structural analysis. Structural design of a diaphragm wall must account for both geotechnical forces and structural loads. The design starts with understanding soil structure, interaction, and external pressures acting on the wall. Key guidelines include 1. Lateral earth pressure. Calculate active, passive, and at-rest pressures using geotechnical investigation data. Wall sections must withstand maximum lateral soil loads during and after excavation. 2. Water pressure. In waterlogged zones, hydrostatic pressure plays a major role. Uplift forces, seepage, and poor water pressure should be evaluated. 3. Structural stability. The wall must be designed to resist bending moments, shear forces, and axial loads. Reinforcement detailing should follow IS 456-2000, ensuring adequate cover and spacing. 4. Durability and crack control. Use high-grade concrete with low permeability. Crack width control is crucial, especially in water-retaining diaphragm walls. Provisions from IS 3370 can be used for liquid retaining structures. 5. Top and bottom restraint conditions. Diaphragm walls can be cantilevered or propped. Wall deflection and rotation must be checked for serviceability. 6. Joints and water bars. Construction and expansion joints with proper water stops ensure water tightness over time. 7. Finite element modeling FEM. For complex sites, FEM can simulate stress distribution and wall-soil interaction effectively. Adhering to these structural design principles ensures a safe, long-lasting diaphragm wall system. Up next, how do we build these walls? Let's explore the cutting-edge machines that make it possible. Advanced machinery used in diaphragm wall construction. Diaphragm wall construction involves advanced equipment that ensures precision, speed, and safety. Here are the primary machines used. 1. Hydromill hydraulic cutter. A high-tech machine that cuts through soil and rock using rotating cutter wheels. It provides vertical precision and is ideal for deep, hard soil conditions. 2. Grab mechanical or hydraulic. A more conventional tool for trench excavation. It uses a clamshell bucket to dig soil and is suitable for softer ground. 3. Desander or desilter unit. This equipment separates excavated soil from bentonite slurry, allowing the slurry to be reused in the next panel. 4. Bentonite mixing plant. Produces bentonite slurry used for trench stability during excavation. 5. Reinforcement cage handling crane. Lifts and lowers large steel cages into the trench before concrete placement. 6. Tremie pipe system. Used to pour concrete underwater through the slurry to avoid segregation. These machines ensure deep excavation without trench collapse, even in complex soil profiles. Each plays a vital role in maintaining alignment, verticality, and wall integrity. With the equipment laid out, let's discuss the materials required to build this engineering marvel. Materials used in diaphragm wall construction. Building a diaphragm wall involves high-performance materials to ensure strength, durability, and water resistance. Here's a breakdown. 1. Concrete, a high-grade mix, typically M30 or higher, with low water-cement ratio and additives for workability. It must maintain flow through Tremie placement and develop adequate early strength. 2. Reinforcement steel. HYSD bars Fe500 or Fe550 are used to form reinforcement cages. They are designed for high tensile strength and corrosion resistance, especially in waterlogged areas. 3. Bentonite slurry. This clay-based slurry plays a dual role supporting trench walls during excavation and preventing groundwater ingress. 4. Water bars and PVC water stops, installed at joints to ensure long-term water tightness. 5. Spacers and centralizers, maintain cage position and ensure uniform cover around reinforcement. 6. Tremie pipes. Though not a construction material, they are essential for placing concrete properly through bentonite. Every material is selected based on site conditions, load requirements, and exposure. Compatibility between bentonite and cement is also tested in advance. Now let's go deeper into the role of bentonite and its importance in diaphragm wall construction. Purpose and requirements of bentonite. Bentonite slurry is the unsung hero of diaphragm wall construction. This naturally occurring clay, when mixed with water, forms a thixotropic fluid that supports trench walls during excavation. But what exactly does bentonite do? 1. Stabilizes excavation. It prevents the collapse of trench walls by exerting hydrostatic pressure, even in loose or granular soils. 2. Seepage control. Its gel-like nature forms a filter cake on trench walls, reducing water infiltration and soil loss. 3. Facilitates reinforcement and concrete work. It allows for smooth placement of steel cages and concrete through Tremie pipes. Requirements as per guidelines. Density: 1.03 to 1.12 grams per cc fresh, 1.15 to 1.5 grams per cc used. Viscosity: 30 to 45 seconds Marsh cone method. pH value: between 7.5 and 10. Sand content: less than 6% by volume. The slurry must be continuously circulated and filtered to remove suspended soil particles and maintain its properties. Regular lab testing ensures compliance with IS and site-specific specifications. The role of bentonite cannot be overstated. It ensures stability during critical phases of construction. Now that we understand all elements, let's walk through the entire construction process. Diaphragm wall construction. Step-by-step process. Let's now explore how diaphragm walls are constructed step by step with precision and control. 1. Guide wall construction. The process begins at the surface with the construction of guide walls to parallel concrete strips, typically 1 meter deep and 0.3 meters wide, built along the trench alignment. These shallow walls help in guiding excavation tools like grab buckets or hydromills, ensuring the trench remains vertically aligned and in the correct position. 2. Trench excavation using slurry support. The next step is the excavation of narrow trench panels, which are usually 2.5 to 6 meters long. This is carried out using either mechanical grabs or advanced hydromills, depending on soil type and project depth. As excavation progresses, a bentonite slurry is pumped in simultaneously to support the trench walls. This slurry prevents collapse by exerting an inward hydrostatic pressure against the earth. 3. Slurry cleaning and reuse. The excavated bentonite soil mix is recycled through a desanding unit. Clean, reusable bentonite is pumped back while the excavated spoil is separated and discarded. This ensures consistent slurry properties throughout construction. 4. Reinforcement cage placement. Once the trench is fully excavated and stable, a steel reinforcement cage, prefabricated on site, is gently lowered into the slurry-filled trench using a crane. The cage is equipped with centralizers to maintain uniform cover and positioning. 5. Tremie concreting method. Now comes a crucial stage: placing concrete under slurry using Tremie pipes. The Tremie is placed at the bottom of the trench and concrete is poured in from the top. As the heavy concrete fills the trench, it displaces the bentonite upward without mixing, ensuring uniform and defect-free casting. 6. Joint formation and stop-end installation. Each diaphragm wall is built in panels, separated by temporary stop ends or steel forms. These guide the concrete and help form watertight vertical joints. After one panel is cured, the stop end is removed and the adjacent panel is cast, ensuring continuity. 7. Curing and quality checks. Once casting is complete, the wall is allowed to cure, and slurry displaced during concreting is treated or reused. Verticality, wall thickness, and joint integrity are checked using ultrasonic or sonic logging techniques. This precision-driven, stepwise process ensures the diaphragm wall is robust, watertight, and ready to support any deep excavations safely and effectively. Stay with us next. We'll explore the benefits of using diaphragm walls in modern construction. Conclusion and benefits. To sum it all up, diaphragm walls are essential components in modern geotechnical and structural engineering, offering unmatched strength, water tightness, and space efficiency. Here are the major benefits: excellent performance in deep and narrow spaces, effective groundwater control, minimal impact on nearby structures, high structural capacity, serving as permanent retaining walls, faster construction in urban or confined locations. With proper structural design, careful material selection, and adherence to its standards, diaphragm walls provide long-term reliability and safety. Their applications continue to grow with urban expansion, particularly in underground metros, basements, and high-rise developments. As technology evolves, modern equipment and improved slurry systems have made diaphragm wall construction more efficient than ever. If you found this video insightful, don't forget to like, share, and subscribe to Civil Engineering Edge for more content on engineering excellence. Drop your questions in the comments. We'd love to hear from you. Until next time, keep learning, keep building.